Y ahora, vale, tengo esto. Espera, ¿me sale? Sí, ya no hay más.
¿No hay más? Lo pongo otro.
Claro, aquí no estoy en medio de esto.
¿Qué es eso? Que te ponga el point el otro.
Sí, porque después intento verlos.
Ah, si no, no te rayes.
What am I seeing here? Okay. Oh. Juanjo, ¿me esperas un segundo? Si yo salgo de aquí de la sesión, si yo salgo de aquí de la sesión de Zoom, no pasa nada, ¿no?
Tú no, tú puedes salir de tu ordenador.
Sí, porque si no, no veo.
Sí, sí, sí.
Okay. Okay, let's see how it works. Because I have to do it for the people home. And are they actually seeing me in this video? This one, obviously. So maybe. I do this and this, and maybe they can see me. Okay. Anyway, it's not ideal, but we will make it work. Anyway, so we're going to start with the demonstration session of the quantum dynamics. So sorry if I don't go, if I don't synchronize myself, because I have to control the Zoom and the online thing with one computer and the local course in here with another computer. So I hope that people home can actually follow. I will try my best. Anyway. So then for this demonstration, I have told you already that we are going to use this Quantix program. So I think that you already know how to connect, so I will skip that, but just in case I include it in here, you know how you can obtain the projects and everything, okay, in here, and then you know how to already send jobs into the queue system. I know that it takes a little time to actually run into the queues. I don't know if you've had that problem before, have you? Okay, so please be patient. The runnings of the program is not super slow, so it's just a few minutes, but we will have to wait for the time that is actually sending the job into the queue, plus the time for the calculation to run. But it's just several minutes anyway. So I will skip that, as I said, and then before we start, I need that you copy. Hopefully everything is okay. I tried with another account that this works, and it did work for the other account. So obviously, I hope that it will work for you as well. So I want you please to copy this file, okay? So this file that is in my account. So I'm SC key. Oh, sorry. I am SCQUI4. So I want you to please copy the bus RC file into your home directory. So just follow that. And just to make it easier, you can exit the account and just log again back. Okay, please remember to include when you connect the X option, okay, so that we can actually export the X, okay, the graphics into our computers, the X means. So once you're ready, so I want you to exit and coming back and tell me if something has changed in your batch, in the terminal that you have. Do you get something like the name of the machine? Okay, so something has changed, and I want you to please type and see if everything works. I didn't do it just for the pretty of the terminal. I did do it because it's friendlier, as I think. But I wanted to add something into your account or into your users in order you to be able to actually run Quantix program. So I want you to please type Quantix just like that and tell me if your path is actually seeing the program. Okay? So please type Quantix, the name of the program. Yeah, it does. It does like do something. It tries to do something. Okay, that's good. So hopefully people home. I don't know if you can actually talk to me. So anyway, so then you are set to run Quantix on your account. Quantix is a free program that you can all download. It's in the Side Hub, I think, or Side Hub, I think. So you just basically have to ask for permission to download, but it's totally free and you can all download. We will do that, and we won't do it, but you can all do it. I will tell you if you need how to do that. So before we start running Quantix, one of the things, if you remember in our Hamiltonian, we have two separate terms or two separate operators. As I said before, we have the kinetic operator and then we have the potential operator. And because we are already accepted and we are under the Bohr-Oppenheimer approximation, we might have obtained before the potential. Okay? Potential in this type of calculations have to be calculated beforehand. So then after that, you start moving the nucleus on this potential. And then the first thing that we have to do is to obtain or to see how our potential is. And we have to set up in the calculation to be read somehow. So what I need you to do is in there as well, yes. So I want you to copy as well from my home directory this input file that is called lsth.inp. It's a very old potential for the description of the H3 system. Okay, so we are going to be studying the approach of a hydrogen atom into a hydrogen molecule. Okay, I don't know if you have been working on quantum systems already. It might be a funny system, but it's a very important system. A lot of people work in this molecule. This molecule or cations of that molecule is a very important molecule in the interstellar medium, and it's very, very wide studied. So there are many potentials in the literature. This is one that is already set in quantics, so this is why I use this one, because I know that it's already working. So we are not going to use the Q system because it's a very fast kind of running, okay? So it might not be worth it to wait because it takes seconds for the running, okay? So the first thing that we are going to do is just to run this program that is part of quantics, this spot feed program here, okay? So we are going to run this in order to create the potential so that our calculations can read the potential and use it in our Hamiltonian, okay? So then if you all run this spot feed space, hyphen MD LSTH, this basically means, and that will be always for the quantics execution, this hyphen MND means make new directory, okay? Quantics and all the programs in this package, what they do is like every time that you run a new calculation, it creates, so you have your, I don't know, if you are in your home or you are creating a folder for this demonstration session, what it does is if you are here and you run quantics, after the execution, it will create a folder in which there will be many files that you will analyze later and will see your wave function, your potential, everything, okay? So this is what it means. Make new directory, NND, okay? So then once you run this, it might have taken a few seconds. I don't know if you've done it already. If you do an LS, you will see that you have all obtained a new directory that is called LSTH fit. Okay, so then I am going to try. I want to be able to do it. Yeah, but if I do it here, you won't see it. Oh my God, that is hard. Anyway, so I will. Yeah, okay. Okay, I go to the next slide and then I'll do it here and you will all do it with me in the session. So have you run it? Do you have already the directory? Okay, that's good. So there is another program that is part of the package that is called showbot. That is the one that is in the previous slide at the bottom, okay? Here, showbot. So in the previous slide, in here, the showbot. Where is it? Where is my mouse? It's gone. Okay, is it here again? Okay, I don't know where my mouse is. On the other side? Okay, I lost the mouse. Anyway, here. So it's this show code. Okay, in the show code, it will show this screen. So the people home, you will have to try yourself, and I will say loud the options. Okay. So then I will do it with the people here locally. So I'm going to connect to. No, not this one. So I'm number 4. Okay, and then I go to school, I think it's called. So if I run showbot, what I get is what you have on the screen there. I'm gonna put this in here. Wait, where is the mouse? I put it in here. Okay. So as you see here, let's see if I have my mouse. When you run this program, it's basically an analysis program or a way to show the potential. is what the name says actually, show laws. Okay, and then you have many options in there. So if the people at home are doing what I am saying, you will see all these possible options, okay? And then we will see how we can plot our potential. Why I want to do this? I don't see my, it's in here, sorry. Because I want you to please first see how the potential looks like. So then first see what is, if we can actually think of how our propagation will go. Okay? So then if I do, this is not convenient doing it this way. How do I do this? Maybe I turn my computer so that I can see this way. Okay. So you see you have many options, okay? 0 is to stop and quit, okay? You have the option number 1 that is plotting into the screen. So if you press 1, it will ask you a few questions, and then at some point it will come something, okay? It obviously, the program is set so that it has some options by default, like some distance, because obviously now we are talking about a molecule that is a 3-atomic molecule. So then it's going to be defined, as I said before, so we have a small r, that is what the program will call RV, vibrational R, just to make it a difference. We have R, that in the program is called RD, dissociation. Small r, sorry. So basically is the reaction coordinate, let's say, because it's the one that is actually describing how the two fragments are approaching to each other. Okay, and then we have obviously an angle that is called theta here. Okay, so we cannot plot the 3 different coordinates plus the value of the potential. So then we have to set one constant. And this is what is given in here. Okay, so if I don't do anything, it will plot x and y, that will be the 2 coordinates, and it will set a value for the theta angle that is 0.792 in gradients, it's not degrees, okay? So then just try and see if it works, and if you see everything, because that will be a, oops. So first thing is 1. So if you, because we are plotting into our screens, so then it says, okay, it's gonna be plotting the potential using contour plots. We all know what contour plots are, like cutting the surface. And then, because he knows how the potential is setting certain values for the cut of the potential. So it says, I'm gonna use a set that is the minimum is this value and the maximum is in this value. If you're happy with these contours, then you say 1 again. So you basically follow what it says on the screen. It tells you that it will plot these contour plots. If it is okay with you, you say yes, and then it will plot something. Did it work for everybody? Yes. Yes? Because yesterday at home I couldn't. The VPN was playing hard to me. Anyway, it's working. Yay! So we have the potential. So we have an angle that is set in 0.7 gradients. Okay. So for me, it will be easier if I plot the potential. But anyway, first of all, what we have that I think I can show it in here. I know because in here I have a. Oh yeah. Something wrong? Yeah. Is it okay? Okay. So in here we have the RV, so this reaction coordinate on the x-axis, and the RV on the other one. So what we see is that we have a channel basically. So we have the H2 molecule here. Okay. If I do a cut here, what I will see is the diatomic molecule, the potential pair for the diatomic molecule H2. Because you are approaching to something that is very far away, so obviously it has to behave as a diatomic molecule. Okay? So then the system will move, because obviously you will approach both fragments, and it will move. and it will reach this point. If we all understand this, and because it's a little bit hard because it doesn't give the values of the energy in each contour plot, but I know that this is a transition state. So basically this is a barrier, okay? So it means that in this angle, obviously here we have a barrier. So our system will come here, and if we don't have enough energy, it will hit the barrier. And what we will do? Going backwards, okay? So one of the things that we first have to check is setting a little bit or checking how the potential looks for different angles, okay? So instead of only plotting the 0.7 whatever, we can just make a set of different potential energy curves and see how they look. So I want you to, the good thing of this is that if you plot again another one, so if you go again one or whatever, it will put as many new plots on the screen. If you don't close it, it will create a new one and a new one, and then you can have a few of them, okay? So then, what I want you to do is, so if you are in this screen, so we go back, if we press the enter, we get back to the main menu of the program, okay? And then if we want to plot different cuts of the potential energy curve, surface, sorry, we have the option number 20, okay? And in the option number 20, what we have is the option to change these values. So then if I type 20, okay, did I? Oh yeah, okay. It tells me that I have to give the values, okay? So I say, RD is going to be X, RV is going to be Y. But now, what is the name? Theta is going to be, I don't know, 0.1, doesn't matter. And 0 at the end. 0, it always says to the program that you want to go to the main menu. Okay? So you put RD space X, RD space Y, theta space 1, and 0. When you are ready, I continue, okay? Is everybody ready now? Good. So if you press that, you come back to the main menu. And then if you press again 1, it will plot another one. So now we have two different potentials. So as I said before, you can have them both plot. Okay? Then I leave them both in here. So people home, you might end up having something as these plots if you choose the radians to be theta equals 0 degrees, theta equals to 30, theta equals to 60, or equals to 90. Just basically just choosing obviously the angle in radians. So if I go back here and I do again 20, I do RD equal X, I do RD equal Y, theta. Yes. Sorry.
This path fit didn't work, doesn't recognize one people response.
Stop me if you can do something, okay? Yes. So the rest of you, please try to do some cuts of the potential, okay? And I'll give you
And another one. Okay.
Yeah.
Because it's not like because now like the parents are like here they show maybe you can stop yeah, right. Yeah, the difference is like Now, what one do you want? You try like 3.4.
Wait a second, people. Can you please
And then please close it now.
can you open did you all copy this file? Did you all copy? Can you open your file, your lsth.inc, and see if you have this number of NAPO basis functions, these 36 and 28? Which one did you copy? No, okay. Can you recopy it again? It doesn't matter because you just take and create it again. Because I've seen that I have a different file in my home directory than the one in my work directory actually. And it's a little bit smaller basis set. So this is why the potential looks so ugly. If you have seen, it has funny behavior in there. So can you please remove, just delete that file and copy the one that I am going to put again in my home directory. Okay, now I put that file into my home directory. Please copy it again and run again the code feed. Remember that if you don't delete the lsth fit directory that is created before lsth fit, okay, if you don't delete that folder before you run it again, it will tell you, I cannot create it again. This directory already exists. So just delete it, okay, and rerun it with the MND, okay? And does anybody else have any trouble anymore? And let me know if the potential looks nicer than before. That is a key, because that means that it's better described. Okay.
No, the one side is for
So remember, you have to redo the pod feed, enter again into the directory, and run again the show pod. It looks better? It does look better. That's good. I need that it looks similar to the one I have.
we change, like for example, like
Yeah. Oh, no, you have to do it. You won't know how to delete a directory, don't you? If you want to delete a directory,
like when I put like 4 days,
okay? Be really careful with that, because if you force this, recursively enforce, it will delete everything. So please write well the directory name, otherwise you will remove everything. Please be really careful about that. Okay? So on my screen now here, and the people home have it as well, you have different plots of the potential energy curve. If you need extra time to do whatever, please let me know and I stop, okay? So now what I have is 3 different cuts of our global potential energy surface. Yeah.
Zero.
You are not.
No, it's also like
Guys, one second, because that will make your life easier for the ones that know, that don't know, of course. When you are on a terminal, let's see if I can get back to the terminal. You are here. Okay, you can go like this, try and look for the command that you have already used, which is okay. But if it is a command that is, I mean, far before, what you can do is just to Control R, and then if you say pot, and then you just write pot, and then you continue to Control R, it will find your command. Okay? It's magic. It's magic. They actually thought about us very much because otherwise we would be typing constantly. So they thought about us massively when they created these terminals, of course. So just for you to remember that you don't have to type. You type it once, it's done forever. No, it will obviously remove your history, of course, at some point. But so now that I have that, I want to go back to my plots for a second. So I have that one. I have, for instance, this one, or I have this one. The difference between them, obviously, is the angle in which we plot, or that the angle that we cast. Okay? So the one at the bottom, that is this one, okay, is for 0 degrees, 0 radians. Okay? The others, I think this one is the first one that I plotted, that it was something like 0.8. Yeah. And this one, I don't remember now. But maybe something in the middle, like 0 point something. I don't remember this one now. And I want you to please check, because that is, I don't know how familiar you are with this type of plotting, but you might be. I'm sorry for the ones that are be, because you are going to be a little bit bored, but I have to explain this. This first plot that we have here is basically some plot or some cut that we have around here. Okay? So it's a cut that we've done on the surface, quite low in the entrance channel, let's say. This is why it's giving the full entrance channel. So when the diatomic molecule is still the predominant in the potential energy curve, this is why it has this shape. Okay? And then once you go to the next contour plot, so the blue curve in here, it will be a cut a little higher. Okay? I know it's obvious because you know that, but the only thing that I want you is just to check that when we get into this region, so the region that is with the circle here, is when we are in the transition state. Okay, so just counting the number of plots or the contour plots that we have, you see that here, with the blue curve, the transition channel is already kind of open at lower energy, let's say. Something that we don't have here because we have 1 and 2. And in this one, we have many others. So it means that the lower barrier is closer to 0 degrees. So if we want to reach the output channel somehow, the reaction might want to go like this. Okay? That is, but we don't choose that. We don't choose that because we create a wave packet, and it might include certain orientations, of course, of the molecules, but the wave packet will move, and because it's evolving, and it's evolving because of the potential, the wave packet will evolve and it will get spread in our potential, and when it actually hits a barrier, will go back, and if it has the room open and free, it will continue opening, but it will propagate and it will spread over the surface. So what do you think that will happen? Will we go in here, although knowing that this curve might be lower than this? Or we will go through this one? What the wave packet will do? What do you think? I mean, you're not getting a mark in here, so you can say whatever stupid thing that it can arrive into your brain. It doesn't matter. So what do you think? Does it depend on anything? What do you think? We are going to create a wave packet, okay? The wave packet, it will be created. We are not in spheres anymore. So we have a quantum system. And then we have a diatomic molecule, okay? This diatomic molecule will have an orientation, or we have a particular value or function that it will be describing something in the diatomic molecule. Don't you think? So one of the ideas is obviously to create an initial wave packet that includes one of the bound states of the H2 molecule. Okay, so this will be something that it will be added into the total energy that we give to our system. Okay, so it's not that our wave packet will be in the bottom of the well. It will be somehow at a certain energy that is the 0 point energy, or the V equals 0, because our system will have to be in a vibrational state. So then that means that we are higher a little bit in here, and then it will move, and then in this situation or in orientation, it will hit the barrier as well as in here. But at some point, if the orientation is good enough, it will reach this barrier, and if it has enough energy, vibrational energy, it will go here. Think that the fact that the molecule, the diatomic molecule, is actually opening because of the vibration, because obviously this will be vibrating from this to this, okay? We are going to be somehow in between these two. So it might reach a point in that it will be allowed to go into that. So that is one of the things that we choose in our initial preparation of the wave packet. If we want to be in the V equals 0, the V equals 1, the rotational initial quantum number J equal whatever, okay? So this is something that we choose when we create our initial wave packet. So this is something that every time that you start doing quantum dynamics in this way, okay, you have to check a little bit how your potential is, okay? And you see if just increasing the vibrational energy, it might help because of the shape that your transition state has. Because not all surfaces are like that, of course. Every surface for every molecule is different, okay? So then you might end up seeing that depending on the orientation of the both fragments, it will help or not help. And obviously the vibrational state as well, okay? So this is one of the main things that you have to check, how your potential is, okay? And an initial idea of how your minimum energy path will be. When you're talking about classical dynamics, that is trivial because most of the trajectories, depending on the energy of your initial trajectory, they will follow the minimum energy path, okay? Because it's the energy and it's sum up, and it will go following that minimum energy path. If you have enough energy that you are so high, the system will move freely, okay? But if you are near something close to the surface of the potential, it will follow the minimum energy path. We all know what a minimum energy path is, no? Okay. So then, now this is all set. And then now we can close the potentials because we don't need them anymore. It's created. So we can close these windows if you prefer, not to have many things open. And then I can continue with the presentation. So this is what you have to do. This is what we end up having. We have already said there is a complete full theory about the transition state theory. There is a theory for the transition state. Just people studying how the system actually behaves in the transition state, okay? So this is a never-ending story. So you think that you are going forward and then you always go back because there are many other things that you can include or study, okay? So this is a full theory. So now, we are going to start actually thinking about running quantities. Now we have the potential, so now we have all set. And then, what I want you to copy again is from my home directory. I want you to copy these three files, okay? h3j0.op, hh2.inp, and runquantics.sh. And you copy it, please, into your home directories. first. We are not going to do anything for the moment, so we are going to do something else before. And then this is one of the articles I think I included at the end of this morning session. Why is my mouse not here? Here. So this is in here, but it's as well in this bibliography slide that I included this morning in the course session this morning. Okay. In there, this is actually some calculations that they did in a paper that was published in 2002 by the developers of the MCTVH, the initial package of the MCTVH. Okay. So in there they define a Hamiltonian. Well, they define the time-dependent Schrodinger equation for this system, and they say that the Schrodinger equation can be written this way. Okay, so they have a Hamiltonian for J and some of the projections of J. I will say a little bit more about that. So when it's plus 1, when it's minus 1, multiplied by the wave function or the wave function. We have already seen this morning. It's okay. And then the final Hamiltonian, it looks like this. So we are going to have the kinetic terms. My mouse is gone again. Here, okay, here. So our Hamiltonian, this might be a little bit more familiar for you. So we have the kinetic operators. Okay, now we have the three different coordinates. We have big R, small r, and we have theta as well for the three coordinates that we have chosen. And then we have the potential, of course, that is the one that we have created already and we plotted before. And we have the kinetic terms related to the three coordinates. And then we have this, and I will show you now what it means. And then we have the other extra terms of the Hamiltonian that are the plus minus 1k, projection of the angular momentum that I will show you in a minute. But we are going to do the example when total J, so the total angular momentum, that I'm going to show it to you now in a second, is 0. So these terms are not appearing, okay? So that, why is not there? I plotted something. So sorry, I didn't. So this is the Hamiltonian. Sorry, the people home. This is the Hamiltonian that we are going to try and. This is a little bit difficult. Anyway, I had some crossings, so we don't need. Obviously, we consider the is back in here. So if we set j equals 0, then the projection it has to be equal 0. So this term is 0. So we are not considering this. And then one thing that is saying is that is giving this Hamiltonian in something that is called body fixed frame. So what does it mean? So as I said this morning, this is a very complicated thing, okay? So you have many ways to define things. So you can be in your lab and imagine that you can actually properly see a collision. You see the collision from your point, so your lab frame, and then you see how things approach to each other. And then you see that this moves and this moves. But you can create as well a system of coordinates that is in the body fixed. So it's in the collision itself. Okay? So we have the difference between the space fixed, that it will be me here, seeing how they approach, or we can define always a coordinate system that it goes with the system. So it's basically intrinsic to the system. Okay? So what they say is that the J, the total angular momentum, is defined in the body fixed frame. So it's here because it makes your life a little easier. Okay? Because everything that will be projected into the system that you are studying. You are not seeing this from the outside, that the vector is in this direction, and then you have to project it into another frame that is far away. That makes everything more complicated than if you have it in here. Because imagine that you are checking all the time that is moving the projection of some of these vectors into this coordinate frame. That makes everything very complicated. But we will need eventually to make this conversion because there are some properties that we have to actually study out of the lab frame. Because if we want to see something related to the orientation of the after the collision, it might be that sometimes you have to define this solid angle that we defined this morning. That is obviously the theta, you remember the theta, and the other one that comes out of the plane. Okay? If you define your body fixed frame, the other angle won't exist because you're always moving with the body fixed frame. So that is something that is a little bit more convenient for the calculation because it makes us to do much lower amount of equations and basically operations. So, oh, there it was. So, do we all know what the total angular momentum is? So you know that is basically the perpendicular to the momentum and the position, basically. Okay. So then we have a J, okay, perpendicular, and then we will have his projections. These projections K, the projections of this total angular momentum J, into the body fixed frame. But we are going to consider that we have total J equals 0, so there is no projection whatsoever. Okay, that these two vectors will keep moving in the same direction all the time. This is why we are in the body fixed frame, and then we are going to consider the J equals 0. That's it, just to make the demonstration a little easier. So, on the left-hand side, so in here, okay, I have included the Hamiltonian. Okay, and it's the file that you call, well, that is called h3j0.op. OP means operator, and the .imp is the input file, and we will go later to it. Okay. So, what do we do with the operator file? So we have it has a format. The input way to add the Hamiltonian into this program. It has a format, particular format in the input file. And on Quantix or MCTDH, it doesn't matter the package that you use, you always have different sections, okay? Each section has to be started by whatever section and might be finished with end section. The of-defined section and of-defined section. All of them. If you don't close each of these sections with the end, the program will try to continue reading something in this section and it will crash, or at least give you some errors, okay? So the first, obviously, the first part of the Hamiltonian, it's something that defines, I don't know why it's not here. Oh, no, this is not my computer, it's this one. Here, in here, is my mouse here, but okay. So the first section is basically a title. Okay, which you say, okay, I'm going to try and study the reactive scattering in Jacobian coordinates for J equals 0, blah, blah, and title and section. You can include several other things, but fine. You will define some parameters. Why? Because for our Hamiltonian, we need masses. Of course, if you remember, in the Hamiltonian, we have 1/2 mass. So we have to define this. The Hamiltonian needs to know which system we are studying. Okay, so then we have to define a mass for the reactive coordinate. Okay, that it will be the reduced mass of the, where is the coordinate here? So then we have this, we have this, and then we have the two different fragments, and then we will have to calculate the reduced mass of these. Okay, so this fragment plus this fragment, not the total reduced mass of the system. Okay, and then this is the total mass of the reactive coordinate, that is this one. But we have to define as well the mass of the diatomic molecule, that it will be the reduced mass of this molecule only. diatomic system. This is why in here we have two different masses. Okay, the mass for the H plus H2 system and the reduced mass of the H2 molecule. Okay, and then we have sum of the angular momentum set to a value. So we have decided that the total angular momentum is going to be 0, so its projection into the body field is going to be 0. And then we are going to set as well an initial value for J for the H2 fragment. Okay, our diatomic molecule, I deleted obviously the curve. So we all know that we have a vibrational state, but we can set as well a rotational state. So then we have set this initial J for the H2 fragment equals to 1. And then it defines this L cent that it will be part of the Hamiltonian later. I will show it to you later for the diatomic molecule. Then we have the Hamiltonian, the Hamiltonian itself. So basically this, considering that this part would be 0, most of it. All this part of the Hamiltonian it will be 0. But this J squared will be different, okay? So let's see how it's written, the Hamiltonian. So the Hamiltonian is written so that in the same line, in each of these lines, okay, the things that are in the same line, they multiply each other. And when you go to the next one, it will sum up, okay? So the people home, the terms in the same line, they will multiply. And if you go to the second, it will sum up. So then what we have is 1/2 mass of the reaction coordinate multiplied by the q squared that this way means the second derivative of this coordinate. So that will be like the kinetic term for this. Okay? So that is like the value that I called it D, they called it D, multiplied by the second derivative of RD. That is what it means. So these two. Okay? We have the same, sorry, in here. So this first term is this first term. Okay? If we go to the next, we need to do a plus. That is what we have to do. It's a minus, but anyway. And then we have the second term, that is this one. Okay? And then so on and so on. And then what we have is that at some point we have this J, and this is what we do here. I want you to please go into the Quantics webpage. They have a webpage. The fastest route to the webpage is just writing Quantics Graham. I'm going to put it in the screen now. Graham Worth. Wait. So you put on your browser Quantics Graham Worth. Graham Worth is one of the developers of Quantics, and is the person in charge of this Quantics code nowadays. Okay, many people contribute, but he's the one actually doing everything. Okay, so I want you to please go to this Quantics. It actually reaches a point that is not what I want. I want you to go to the main. I'm going to show it to the people home here. I can go to the, yes, here. Quantics, oops. Graham Worth. And then you go to Quantics webpage. You go to the main menu. And then here you have everything, all the documentation. I mean, the program is massive, so there is a lot of documentation, but it might be a lot of things missing. But for our demonstration today, is more than okay. So I want you to please go for a second into the Hamiltonian documentation, and just going down, I will put it in a second there. I want you to please go down into this, and at some point you have this, that it downloads a PS file Okay, have a look at the file for a second. Oh my God, you cannot see a PS on a Windows computer. I don't know. This, let's see if it looks this. Okay. I don't want this. It doesn't show it. Okay. Okay, I cannot do much in here. I'm sorry. I don't know. Windows computers always plays funny with me. Anyway. So if you download home, just have a look at the file, okay? So in here, if you go to the Hamiltonian section, sorry, and then you go down on this, at some point you are going to reach a link that is called built-in symbols. These ones. Okay, and this is where all these symbols that I have shown before, like j squared, k to the minus whatever, are actually defined. So in this file are all the things that are built in the program that are like shortcuts that you don't have to define the derivatives or the things yourself. Okay? So in here, it's so little, sorry, wait. 100. Can you see it on the screen? 150? Let's see. So, j squared is here. So just putting j squared, he knows that he has to do these operations in the Hamiltonian to the wave packet. Okay, he has to apply these operations into the wave packet. And he knows how to compute it. Okay, because of the type of basis set that we are using. Okay, everything is set up. But you need to know, obviously this is why these programs are not that easy to use actually, because you need to know a little bit how to set your Hamiltonian so that you can choose the type of operator and the type of application that you can do. But in the way that we have defined our wave function, he knows that if I put j squared, it has to compute this. Okay, so you have all the built-in symbols, they call them, on these documents here. So I can just close it. The same for the key A and the key E. So you see is the -1 divided by 2m, the second derivative. So all these symbols are already set. So it makes it easier, at least for the Hamiltonian, to be set. Let's go back to the here. Okay. So now we have set, and obviously at the very bottom, the potential that is here. Okay. So the potential here, that is the one that we have at the very end. We have set more or less our Hamiltonian. Is the full Hamiltonian that will be applied to our wave packet. This is one piece of it, okay? But if you remember what I said before, is that we have to set our initial wave packet. And our initial wave packet, it has to be formed by a vibrational state of the diatomic molecule. The vibrational state of the diatomic molecule has to be calculated because it is not set. You can have H2 plus whatever, but you can have F2, whatever. Okay, so then what you do is, if you go to the next slide, okay, so what you do is just to include another Hamiltonian section that is devoted to the H2 molecule. So this fragment here. Okay? And then what you said is the Hamiltonian that you want to apply so that you obtain the vibrational states of the H2 molecule. Okay? So then you will have the kinetic energy operator, that is the second derivative, and because the way that we have defined, we just have to include Ka, and because we have defined the mass of the system as mass underscore the name of the variable, he knows that the mass is the one in there. Because it's mass, the name of the coordinate. The name is important, so the format is very important. If you don't use mass underscore the name of the coordinate, you cannot use this Ke operator like this. You will have to write it like 1 over the mass minus 1 over the mass, derivative, second derivative, whatever. So what we did in the other one. So you see that here is not included as key A. Okay? So it all depends how you define your system or your wave function. And then it has the potential. So what it says is that it's going to use the eigenvalues, the vibrational eigenvalues of the H2. This is what it means in here. And then something that is related to the J, the small j. That is the one that we defined before. You remember that at the beginning, then I have Lj, that L said that it was equal to 1/2 in the projections. So now this will help us to start creating an initial state for the diatomic fragment. How do we define this coordinate? Any idea? First, if you remember from this morning's session, we have to set a wave packet that has certain values of energy, certain values of momentum, blah, 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 blah. So what we do is just to define a function that is a wave packet with different energies. Okay, so what we basically do is we create kind of a Gaussian function or this type of function that what it does is like, so you have your potential. Let's see how I do this. Imagine that we do a cartoon 1D in our potential. It's going to be something like this with a barrier, okay? And then what we have is we have a packet of energies. I'm not the best drawing, I'm sorry. So our wave packet now, it has a set of energies. So this is what ensures that if I have enough energy in my wave packet, if I reach these points, some parts of the wave packet will go, but some will hit and go back. So then we have a full set of energies that will allow us to calculate what happens after a collision with different values of energy. So this is the idea of a wave packet, basically. Obviously, because we cannot create hard spheres, because now this is a proper system, then we have to create a wave packet that it brings different energies for the collision, so proper momentum, okay? And that will give us an uncertainty in energy, if you want to call it, okay? And it will be directly related to the time. That is what we see in this morning. I'm sorry, but you don't see that. Probably, I don't know if you see this on the blackboard. So now that we have the operator file, what we can do is just to go to the input file, because so far the only thing that we have done so we have H defined, but we don't have our wave packet, wave function or wave packet defined yet. So we need to define the wave function. So the wave function will be given, or the ideas of the wave function will be given in the input file. So, because I said this morning that this program, what it does is just the wave function or the wave packet is created as a combination of Hartree products, okay? The Hartree products are basically multiplications of different functions that we can call them orbitals. This is the same that we do in electronic structure calculations. So when you have a Gaussian function that you send into the Hamiltonian to be set, so what we do is just, we have different functions, Gaussian functions. So here is going to be something similar. So then, the first part of the input file is again the run section. So in there you will say, what do you want to do? Because there are many things that you can do with this program. So one of the things is, let's see here. So you give the name of the output directory name that you want. I don't want you to put H2 and J1, but anyway, just give a name to the directory that it will create when you will run, okay? The one that you prepare. We say that we are going to do a propagation because we are using this operator, this evolution operator. And we say that we are going to run it for 120 femtoseconds, quite fast. That we are going to start, that we are going to write into our wave function every 1 femtosecond. And this is in the output file, and this is how we are going to write it into this side. We will create several files, and I will show it to you. And then some of the things here is just like I want you to write sine wave function into a file, the population of the grids, and some steps. Okay, a title and something related to some fast way of running this. Then you go to the operator section. Basically, when you say, I want you to use the operator that I have just created, that is the H3J0. Okay? The next thing is related to this complex absorbing potential that I talked this morning. It's called complex absorbing potential, or a CAP. We call it CAP all the time. Okay? And then it has certain values. So it says that the starting point, so this first CAP that is in the reaction coordinate, it will start at a distance of 6.04. It has a strength and it has an order. So it's obviously a function. So the function has an order and it has a strength. The strength is obviously the ability of this complex potential to absorb the wave packet. We have set the absorbing potential for the reaction coordinate, but as well for the diatomic distance, okay? So then if you remember how it was the potential, that it was something like this, and if we are in 0, we have something like this, okay? So we are setting one here and another one basically here. So because we don't have an infinite grid, okay? So we have to set, just in case our molecule breaks, our diatomic molecule breaks, is trapped as well by another. The other thing that we say is that we want to use the potential that we have created, the port fit, okay, that we've created, that is in this directory, LSGH fit, that is the one that you've created already. And because it's in the same directory, please be really careful that the input operator and this directory LSH fit is in the same place that you are running your calculation, please. Otherwise, you will have to include here the path where this directory is, okay? And in here, you can put as many labels or things that you want to alter coming from the operator section. So not to change. So if you have set your operator, Hamiltonian, already, you don't have to change things there. If the only thing that you want to change is a certain value. So you have the option to alter some values in the input file so that you don't touch the operator. When it works, don't touch it. Because that's one of the maximum things that you have to do. If it works, don't touch it, ever. Okay? These Hartree products that are these orbitals, okay, is what we call in quantics single particle function. So it says how many orbitals, how many Hartree products, how many products you want to have in your Hartree. This is what you set up in here, okay? So I want to have 14 for the dissociation, 10 for the RB, and 10 for the theta. So we are setting the number of functions, just like that, only these. Okay, so the cups in here and the Hartree products in here, basically. So if I go to the next slide, is the continuation of this file. So it has several more other things. Obviously, we have defined the function, but we need to define our grid as well. So we need to define the type of function that we want to use, because as I said, you can use a Gaussian, you can use, I don't know, something that you can actually derivate with a Fourier transform. You can, so you have to define the type of function, the type of function. So you said how many functions you're going to use with a single particle functions, but now you have to say, I want it to be a Gaussian. I want it to be whatever. I want it to be a vibrational state of the diatomic molecule. Okay? And this is what you do in here. Okay? So basically, we are going to define RD and RB by a Fourier transform type of basis set, although they are called SIM. This is in the input, in the documentation, you have all the options that you have. So if you go to the documentation here and you go back to the main menu and you go back to the input documentation, you will see all the possibilities that you have. Those are some variables already set. And this is the rank section. And at some point, we will have the primitives at some point. The operator, this is something that, so these are the single particle functions, how to use it, multi-layer, the primitives. So you see, you have all these sort of functions. Okay, I'll show it to you, the people home. Wait, here, so you go back to the main menu, you go to the input documentation, and then if you go down, 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 dynamics, in here, you have all the primitive possibilities that you have. Okay, so you can choose harmonic oscillators, you can use a legender DDR, an FFT that it will, is similar to this, so it will run a Chebyshev propagation. That is one of the things that I mentioned this morning. So you have all these extended legender polynomials that it will include the projection, the angular momentum and everything, okay? All this, obviously, as you see, is a very big program. Okay, so now we have everything set. We have already more or less understood a little bit the input file. So let's run the calculation. So if you have, I have included it in here just in case you didn't have the time before, but just copy the input file and the operator file and the run quantics, if you've done it before, you don't have to do it anymore, and then run the calculation. And we run it like with the SBatch, the server, the partition, choose the one that you prefer or the one that is going better this morning, and you run quantics and the quantics shell that I've included before in here. I think let's try, but I don't think that it works. Where is the choke again? Yes.
The only partition that works for BioSync server is BioSync.
You have to write
because
BioSync.
I did, yeah, but this afternoon when I tried, the BioSync didn't work. This is why I put this one, but it's okay. Choose the one that you prefer.
It's the only one that works because those are complex machines and you cannot use it.
Yeah, no, but I ran my calculation with this afternoon.
It happened. I have another error. I do it.
Okay, I'll go in a second. The only thing that I want to tell you is that these run quantics, can you please open the run quantics a second? That you have. So you see, wait. As you see, these will be waiting the input file, okay? Because before I have it in here, but just in case I didn't want you to constantly open the file, I included the file that you can send it on the SBatch. So then instead of the other one, just use this one. Sorry. SBatch minus A by wait, I might have it here. And at the very end, you put hh2.inp. Okay? And then run it. Be patient. It might take a little time to get into the queue system, and it might take a little bit of time to run. Okay? So we will wait for everybody to finish. Yeah. Guys, wait a second, please. So, if you see here, I don't know if it's happening to the people at home. I will try and show it to you in a second, okay? If you see here, I have a directory that is called school. I'm very imaginative, as you see. And then in here, if I do ls, okay, I have the input file for my potential. I have the input file for my propagation, and then I have the operator file. But it has to be in the direction before the LSH feed, because what we have said before is that our potential is in this directory. So if you are inside this directory, nothing will work, because it's going to look for this directory in the running, and then it cannot find it. So the inputs, the operator and the input file has to be in the same directory in which you have the LSTH feed directory, okay? And then let me know if it runs. It does?
Yes.
Okay. It takes like 5-6 minutes, I think. So is everybody having any trouble? No? So for this one that is running, I might excuse myself and go to the university. If anybody needs
Porque ya está.
Something about this like they told us, any other girl presents, you're not going to accept more guys to present because it's like 7 guys and 2 girls. And like you said me yesterday, and I present something and so on. I was like, okay, how much that I didn't do it, you know. Like a little ago. So I said, no, can today. And he told me, no, you focus on the thesis and that's it. And after writing again, it's like, if you don't present, Santiago and I can't present. And I was like, Marcelo told me no. And he said, oh, so Santiago can present and put a sad face. And I was like, oh, I'm so sorry. I couldn't care less. I didn't say that, but yeah, that's the truth. It's
Did you get the output already? It didn't run? Marta, did that? Is it still running? I don't know if the people home, if you have any questions, just send me an email. Anyway, it's still running, but anyway, we will. I will show you something on the screen here. Can I actually, Juanjo, in this computer, do you have a MOBA X-term or something? Something to connect into the CCC? The MOBA, no? Ah, Putty, well, Putty, whatever. Host name is login 1 CCC 1 that is. So I hope that you managed to actually run the calculation, and then you might have already this directory, okay? If you haven't, you will eventually, I don't know, and then you might not have as many files as I have, but it doesn't really matter. No, not in this one. CDLS fit. Okay. No, it's too late for me as well. HS2. Okay. You might not have as many, but you might have some. I don't know if it ran and it finished. You might have some of them, and you can open them. So let's go a little bit through them. You might have already an FD. I will tell you in a second. You might have a log file. You might have an operator file. You might have the log of the operator file. You might have an output. You have to decide that this is our wave packet, okay, written into the disk. So then we can plot it. We can play around with it. We have something if we will want to restart our calculations, something related to steps, timing, and whatever, all the things, okay? The log files obviously give you information about how the calculation is actually having troubles or not, okay? So those are readable. If you open them with an editor, you will see that it's readable. If you open the others, you won't see anything because they are binary files, okay, just to save some space. But let's have a look at the output file, okay? The output file is as well something that you can actually read, okay? And it's writing into the disk how the calculation is going. So it gives you information like the time step that you are in, the total energy of your wave packet, so where it's actually placed in your potential, and it's including the energy potential, the potential energy, okay? The CPU time, the norm of your wave packet, okay? And if you remember, I don't know if you remember, but if you remember a little bit, the number of single particles functions that we have used to describe this Hartree product are the ones that we have here. For the RD, we chose 14, I don't know, 10 and 10, and those are giving you the population in each of these, like the population that you obtain when you run a electronic structure calculation, that it gives you the population and the value of the energy of the orbitals, similar here. And the ones that are more important for our calculations, okay? So the first one will be very important, and the rest will be decreasing, okay? But they will be necessary for the whole propagation, because it might be that for the definition of the initial wave packet, that is the time equals 0, we only need very few functions to define something so pretty as this. But obviously, when it evolves in time, it's spreading, and obviously you need many more, okay? So there is a program to analyze how the population of these states, because obviously you need to converge the number of single particle functions in every calculation, okay? So I don't have the time to do that, because it's already 25 to 8, so I don't want you to be too bored anyway. So this is something that you will have, the same way that you converge your electronic structure calculations using different basis sets, the same. Okay, is the size basically of your basis set. But obviously, because it's evolving time, this population will be changed over the time. What else? It gives you the expectation values as well. Here, okay, at each time. So it tells you that because you have set actually your wave packet in a place, it says that for the dissociation coordinate is the expectation value is 4.5. That is actually where we have set this. Okay, so we have put the two fragments as far as 4.5 angstroms. Okay, to start the propagation. It might be too close, but for this type of course, it's not enough. The expectation value of the molecule, the diatomic molecule. I don't know if you know, but the H2 molecule has a minimum in 1.4 atomic units. Okay, so this curve has a minimum. What do I do with the chalk? Here. Maybe it's easier if I leave it here. This is 1.4 atomic units. So our initial wave packet is well done, okay? So the expectation value is 1.4. That's good, okay? And the theta is set into 1 at the beginning, okay? So then if you go down in the file, so in here, okay? So the population is in here. Well, the expectation values are in here, okay? So if you move down till, I don't know, you reach a certain value of time, I don't know, 25, 20 seconds, you see what I said before, that the populations of your single particle functions are not zero anymore in the larger values, because obviously the wave packet is spreading for the whole, and then your expectation value is changing. So now we have come closer, and for the expectation value of the diatomic molecule, the molecule is vibrating. So the propagator is doing what it's supposed to be doing, because obviously it's affected by the potential. So when they are getting closer, it's doing like this and getting closer, and then the energy as well changes. Okay, so it's something that you can all check, go through the output and see what you get. Okay, so this is basically how the output looks like. So let's do something that is funnier and nicer to look at. So, because we have many other files, one of the things that we can do, obviously, because we have the wave function or the wave packet, we can plot the wave packet and see how it evolves with time. So, Quantix includes some analysis programs that they are nice enough to make very easy names, so just called analysis. Okay? And it has a similar structure as the one that we use for the shortcuts. It's certain values that you can choose in order to see whatever you want to see. If we want to see the evolution of our wave packet, then we go to the option number 5. Okay? And then in here, what it's going to do is to tell, well, to ask, what do you want to do? You want to do a plot in 1D so that I make cuts in the wave function with 2 of the coordinates constant? That would be a 1D. Or only choosing one that is constant, and then you get a funny plot and things. Just to make it, hopefully, we don't actually crash the CCC, hopefully. Let's all try. Have you all connected into the different logins? Login 1, 2, 3. I hope that you have done that and it doesn't crash anyway. So let's do the number 2. Be patient as well for the ones of you that your calculation has finished, because it takes sometimes a little while. It's not too big, the wave function, but it might take a few seconds, okay? So as before, you have all sort of options here. I'm gonna do it for the people home here. So just run analysis, number 5 and number 2, and then you end up with this, okay? Now, because we have something that is evolved in time, we have the possibility to actually make a movie, okay? Similar to what Basile was showing to you before, that he was showing the molecules itself. Now our molecule is a wave packet, okay? So then, because our wave packet now is evolved in time, we can plot as a movie. So we can do, as before, a cut in either coordinates, and we can choose theta or RV or RD, okay? And there is something as well that I like. I think I like it better. Instead of seeing the wave packet moving as a contour plot, I wanted to see it in 3D. Like I have a proper function that I can see instead of cut, because the cuts are okay for the potential, but maybe for this it's easier to see on a 3D type of plot. So if we want to use surface instead of contours, what we do is just to use option 160, okay? And then if you see, some of the options have changed. So now it says that the surface is on, okay? And then it will plot the surface plus the contour plot at the very bottom. Then the option 285, I won't go through all of them, so you can check later, okay? By the finish, well, till the finish of this session. It says that every time that I push the enter, it will give me 1 after second, okay? One femtosecond, 1 femtosecond, and I will see the evolution of the wave packet every femtosecond, okay? So what I have it is like step through. Instead of having a movie that it runs, I can do it with pushing the enter button, okay? So this is what I'm gonna do. So I click 1, that is always the option to plot on screen. This is what I want. Obviously, if you want to save it into a file, you can do it later, but when you have decided the movie that you want to actually save. So they actually tell you, I am going to compute the densities. I'm going to compute the square of the psi function, okay? So at the same time that it will plot you the wave function. It has to compute the square of the wave function, okay? So it says this might take a while, okay? I mean, it takes a while, but it's doable. At least it was doable before. Yeah, it does. It did work or not? Of course, now that we are here, it's never going to work, is it? Okay, now, 1, 1. Here, I have it in here. Wait, where is my mouse? Here. There you have a wave packet. Pretty, isn't it? So, if you remember, I said my wave packet for the dissociation coordinate set up in 4 point something. Okay, is a wave packet. Is the square? Remember, is the square? So we are not seeing anything like this. So we have like a beautiful type of Gaussian shape. Okay, and then if we click, we are going to see how the wave packet evolves. I have to be here. Where is the mouse? Here. Let's do this a little smaller, or here. So then we can have both at the same time. Okay. You see, at this point, the wave packet has reached this. So it cannot continue, obviously, because it reached a barrier. So it looks for a way to escape the barrier. And obviously, because I am plotting 0 point something, I don't remember now, that is not too far for the value of 0, that is when our barrier, it was lower, is going to escape in this direction. Okay? Look. But obviously, the portions of the wave packet, the initial wave packet, because as I said before, we have a wave packet that it has a packet of energies because of all this transformation that we spoke about this morning. Okay, some will hit the barrier, but some others will be able to pass. And this is what is happening. Our wave packet is coming backwards. And some part of our wave packet is escaping through the output channel. Okay? So then you can continue. The propagation will finish when you reach the 120 femtoseconds, of course. But something that I want you to take into account is that we haven't said that the z-axis is fixed, like from one value to another value. So then automatically decides that it can change, just to show you the wave packet as big as possible. But that makes a little bit things a little bit more complicated to understand the absorbing potential, because we are not going to see that well. So we will do an extra plot in a second, okay? Just for us to see. So as you see, I put an absorbing potential at some point in here and in here. You remember that I put two absorbing potentials? So then it reached the value for the absorbing potential. So you don't see it because the scale is changing, but the wave packet is being absorbed on the edges of the grid. So then if you continue, you see that the z-axis is decreasing. You see, 0.4, 35. So the packet is being absorbed. Okay? And at some point, we have a very little density of our wave packet because it's being absorbed. Okay? Finish. We reach 120. And if I put that on the top, you see that the density is very small. So if instead of doing this, what I do is I go to one of the options in which I have the set. It might take a while. Did I find it? Wait. Javi, where is it? Which option is it? The z-axis? Oh, here. The 70, no? Yeah, 70. So maybe, oops. So the maximum is 379. So then I put this value from 0 to 379. I push 1 again, 1, 1, and then again my wave packet is here. Again, oops, wait, I move it a little bit here. Again, it reaches the barrier, it escapes to the other channel, and it's been absorbed already. Look, that I barely see the wave packet. So after 40 or 50 femtoseconds, we basically have no wave packet whatsoever. It's being absorbed. So then that way we are sure that nothing, no numerical errors are coming from the fact that it's coming here and coming back here, or reaching this and coming back from this other side. This is why they are needed. I don't know if you managed to do this. Yes? I hope that people from home can do it. So let's do it for you guys. So I choose the option number 160. One, it might take a while. And then the only thing that I am missing, just for you to know, is obviously try and get the probability, okay? That is the property that we needed to actually, at some point, compute the cross-section. So this is what I'm going to do in a second. It's not working here. It takes a little longer here. Okay. Oh, it doesn't work. The putty doesn't work. So just try and follow these options, and then you will see a beautiful wave packet. And if you press the enter button, you will see the wave packet propagating. It's because of I don't have the server here. Anyway, so the other thing that is missing now, just for you to see, you remember that when I showed this morning the population, the probability equation, you remember that one of the things that I focused on, it was on this delta E, that it was in the lower part of the fraction. You remember that? That I had I have a problem with the chalk. Anyway, so you remember the probability, we have something that it was something here and it was a delta E here. This is a way in which, obviously, for the set of energies that you start with, what you want to know is the probability that you get it in this amount of energies, okay? So you have a distribution of energy coming from the initial wave packet. And this is something that we need to have in here, because we will use it to compute the probability. So if you all have it, but I suppose you have it because you have run the same thing that I have run. So what you need to run is the option flux, okay? And then, because I have my wave packet like this, that it comes from one energy to another energy, if I Fourier transform from time to energy, I want you to put 0.4, I know because of that, but otherwise you just plot the energy, this file, to 2.0, okay? I think that you can actually plot it here, but I'm not gonna do it now. So if you put 0.4, 2.0, with commas, I think it is needed, 2.0. In electron volts, it tells you, do you want me to use a specific cup? No, just sum all the cups. Okay, it's fine. It doesn't show into the screen, but it created a file that is called flux. Oh, I might not have created mine because I have to run it minus W, 0.4, 2.0, EV 0. It takes a little while, but not too much. And then we have this file that is called flux. It's what I told you. We get the probability out of the flux coming through the absorbing potential. Okay? It's the way that this program does this job. Okay? So then in this file, if I make it a little bigger, if I can, it's not, okay, this way. It's not working. Why is it not working? Anyway, what is wrong with this? Okay. So what it gives us is the flux itself. So the flux coming out of a perpendicular surface that is actually summing up everything that comes through it. Okay? Like if you pass through the door many times, so many people, and if I am there and I see people coming out of a room in here, I see the flow. So this is the flux of people coming in and out. It might be one, or it might be 2 or 3 of you together. Okay, so this is it. This is the flux. This is the delta A that I told you before, because we have to obviously divide by it. And this is all the job already done. So this is the probability. I don't know the one that I have here. I don't know if I've done the right one. Maybe I just made another calculation because I don't like this flux. No, this is not the one. So probably if you have run the calculation, maybe you can do it because this is another run that I did with a different value of J or B or something. If you have it, did you have your run already done? Try and plot the 4th column, okay? Or, oh no, it doesn't work. So try and do this, and then you will see a nice probability that is completely different to this one. I hope that you get it. Better than if I put something into the input file, otherwise we run it again. I'm going to try and run it myself. Do you see something similar to what I had, or? It's because I tried this one, I think. Let's have a look. No, it's already running good. So, did you manage to do the calculation? We're gonna be finishing in 2 minutes. If it doesn't work, you will see it later. But anyway, it's just because I wanted to show you the probability, because it's a nicer thing to see. Oh, you finished already. That's good. Oh, this is the check-in that I was doing before. It's not J1, but it's fine. So I do the flux, 0.420 EV, sorry, 2.0. This is not 2, I don't see it. Ah, it's because it's folded there. EV. It didn't run. This is not the one. It didn't run for some reason. It said that it ran, but it didn't. I didn't get the, so it actually didn't work. I don't know why. It has to be something like this. I'm sorry that I don't know what I made, because I've been doing so many checks before that I might have touched something. So the population, probability, sorry, not population, probability as a function of energy. I will do it later, and then you will have it on my home directory, and you will copy it maybe tomorrow. So then we had something like this, and the probability increased. Okay? So what do we get from this? So what we are getting is that we are obviously increasing the probability of obtaining the process that we are actually studying when we increase the energy, because obviously we can overpass the value. Okay? I will do it maybe tomorrow morning. And then I will send an email or whatever, so that you can actually plot the first and before, and then see this. And then you can check that you have an energy distribution that is like this, and it's obviously defining everything well. I don't know where it didn't work now. Sorry about that. Not everything could go well. So you will see that the probability will be increasing for the value of, for the energy, of course. And then obviously it tells you that with the higher energy, you get higher probability, of course. One of the exercises that you might try is just changing the initial J for the initial eigenvalue or eigenstate of the diatomic molecule, or you can increase the values of the energy for the energy distribution, so the momentum, the initial momentum, okay? Or you can try and see how the wave packet actually behaves. Try and increase the vibrational state so your molecule is more open, and see how the wave packet actually evolves. So you have it all set in your user and your home directories now. It's going to be there for all the time that you have the user in there and the account. So try and run it. And if you have any problem, just write an email to me, okay? And then I can help. So I hope that you enjoy. Although this is not set yet, but that you have understood what a wave packet is, how you can see how it evolves in time, properties that you can get out of it. Try and play with quantics. It's all set there for you. So I leave you alone. It's 8. I couldn't do it better in time. So I'm sorry for the people home that I couldn't show you the wave packet. I hope that you managed to do it yourself. So if you have any problem, just write to me. Okay? I don't know if you have my email actually. It's in the webpage of the, no? So my email is very easy, it's my name basically. Cristina Sanz at, okay. If you wish, I'm here, and I'm not going to be here for I'll be here tomorrow, but I have to leave on Thursday. But if you need any help, just write to me and I will help you happily, okay? No sé por qué no ha funcionado esa, bueno, da igual, si lo pongo.
Te damos tu diploma oficial.
Bueno, que tengo un diploma.
Hombre, y un regalito a los profesores. Bueno, es una miseria.
Muchas gracias.
Somos pobres.
Bueno, sí, yo me imaginaba que no me ibas a regalar un Rolex.
Eso estaba guay.
Qué lío con las pantallas. Bueno, al final más o menos, lo único que no, el cookie no abre el servidor X. Entonces no se puede enseñar, pero lo demás más o menos eso lo estoy haciendo. Más o menos,